Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about carbon dating. So what is this carbon dating? Radioactive dating or carbon dating or carbon 14 dating, it is a scientific method that can actually determine the age of a organic material or any fossil as old as approximately 60,000 years. Now, it was first developed by Willard Libby in late 1940s at the University of Chicago, and the technique is based on the decay of carbon 14 isotope. And he also won Nobel Prize later on because of this discovery. So, what is the technique? So, what happens is that every living being or every living thing is made of carbon. So, if you look at the video, so this plant, they grab this CO2 from the outside and use it to form some complex molecules. The animals eat the plants and then they get the carbon from there. But there are more than one form of carbon. So, a typical carbon atom will consist of 6 protons and 6 neutrons. We call them carbon 12. Now, high above the atmosphere, these cosmic rays, they hit this nitrogen atom and create a carbon which consists of 6 protons but 8 neutrons. We call this carbon 14. Now, both carbon 12 and carbon 14, they behave alike, but there is one attribute that separates this carbon 14 from carbon 12. Carbon 14 is unstable. And when a person dies or when an animal dies, this carbon 14, it disintegrates. And it takes approximately 5,730 years to reduce this carbon 14 to half of its size, and we call that the half life of carbon 14. So, after 5,730 it reduced to half, and again another 5,730 it becomes 1/4, and then it becomes 1/8. So, scientists use this information to calculate this approximate age of the fossil or of animal, plant, trees that absorbs this carbon 14. So, let us see that how we can use this mathematical modeling to find the approximate age of a fossil or of a relic that suddenly the archaeologists discover. So, to start with, let us say an archaeological sample has been found . And whose age needs to be determined. So, we consider let AT is the amount of carbon 14 present in the sample at time t. So, please remember this carbon 14, when the thing is living, there is no problem, but when that thing is dead, then this carbon 14 starts disintegrating or leave the body. So, the differential equation which will follow this will be given by dA dt is equal to some lambda times A, and we call it a radioactive decay law. Now, this is quite easy to solve. So, you separate the variables minus lambda dt, you integrate both sides, this will ln A minus lambda t plus some constant, and let's take it as ln A0. So, we will get ln A by ln A0, sorry, ln A minus ln A0 and this is equal to minus lambda t, which is A by A0 ln equal to minus lambda t, which implies A equal to A0 e to the power minus lambda t. So, this you can write as AT. So, AT gives you the amount of carbon 14 present in the sample at any time t, and this A0 is the initial value. So, we can say A0 is A0, which is the amount of C14 present in the sample when it was discovered. Now, say if we want to calculate what is the rate of disintegration, so we have to find this dA dt, say we name it as mt, and we get, so since the rate is reducing, we put a negative sign, we get something like A0 lambda e to the power minus lambda t. So, if you want to find m0, it is A0 lambda and the ratio mt by m0 will give you e to the power minus lambda t. From here, you can calculate this value of t is equal to 1 by lambda ln m0 by mt. So, m0 is the original rate of disintegration, at time t equal to 0, and t gives the age of the sample, provided you can measure this m0 and this mt. The same can be told from here also, that from here we can get this AT by A0, which is equal to the power minus lambda t, and then from here also t you can calculate ln AT by A0. So, you can calculate the approximate age of the given sample either using this or using this, provided which information is available to you. Now, let us quickly define what is half-life. So, half-life is the amount of time required by the disintegrating or decreasing substance to reduce to half. So, we have the equation AT equal to A0 e to the power minus lambda t. So, where your A0 is the amount of carbon 14 that was present in the sample when it was discovered. So, what happens when this reduced to half? So, your AT becomes A0 by 2 and time, say we represent at tau. So, this becomes A0 by 2, this becomes A0 e to the power minus lambda tau, where tau is your half-life. So, this will give e to the power lambda tau equal to ln 2 and sorry, not e to the power lambda tau equal to ln 2, and your tau is equal to 1 by lambda ln 2. So, this gives the formula for half-life. Now, let us take an example that how we calculate the age of a fossil or a sample or an archaeological sample. So, an example, say a fossil is found that has 20% C14 compared to the living sample. So, how old is the fossil? And it is given half-life of carbon 14 is 5730 years. So, you have the formula, which is AT is equal to A0 e to the power minus lambda t, and it is told that you have 20% of the carbon 14 present compared to the living sample. So, basically this ratio is going to be 20 by 100 or 0.2 equal to e to the power minus lambda t. So, 0.2 is 1 by 5. So, e to the power lambda t is 5, and this gives us lambda t equal to ln 5, and so your t is ln 5 divided by lambda. Now, we name it as number 1, and also the half-life tau is given by ln 2 divided by lambda from this particular formula. So, from this and this we eliminate this lambda, and you get t equal to, so I just get lambda equal to ln by t. So, this t will be equal to tau ln 5 by ln 2. And if you substitute all these values, this is 5730 multiplied by ln 5, which is 1.6094 divided by ln 2, 0.6931, and after simplification it will approximately give 13305 years. So, that the age of the fossil is approximately found to be 13305 years old. So, that is how the mathematical model for this carbon dating works. We now look into another example, say an archaeologist digs up a human skull. At a dig site. The age of the skull is 11460 years. So, we have to find what is the concentration of this carbon 14 of its initial condition. So, if the concentration of carbon 14 of its initial concentration be x, then what is the value of x? So, our governing equation is AT is equal to A0 e to the power minus lambda t, where your A0 is the amount of C14 present in the skull when it was discovered. So, we take log on both sides. So, you will get e to the power minus lambda t is equal to AT divided by A0, and this will imply minus lambda t is equal to ln AT by A0, and this implies t is equal to 1 by lambda ln AT by A0. Now, I have to get an expression for this lambda in terms of the half-life. So, what is this half-life? It is the amount which reduces to half of its size, and we have the time tau. So, tau is the half-life in which this initial concentration reduces to half of its size, and this will give me this, and this will cancel, e to the power lambda tau equal to 2, which will give lambda tau equal to ln 2, and which will give lambda equal to ln 2 by tau. So, I will put this value of lambda here. So, we have from here e to the power minus lambda t, that is equal to AT by A0, and this value is the concentration of x percentage, and hence this will be x divided by 100, and I have to calculate this value of x. So, therefore, the value of x is 100 multiplied by e to the power minus, in place of lambda I will put ln 2 divided by tau and multiplied by the time, and that time is 11460 years. So, the value of x is 100 multiplied by e to the power minus ln 2 divided by tau, which is 5730 half-life, multiplied by the years, which is 11460. And if you simplify this, this will be 100 into e to the power minus 1.386, and this is approximately equal to 0.2500, and which gives your answer to be 25%. So, the concentration of the carbon 14 to its initial concentration is 25%. We next move to another example. A museum is testing the authenticity of a Leonardo da Vinci manuscript, which is supposed to exist between this period. So, the museum send a paper sample to a lab in 2022 and learned that it has 97.4% of its initial carbon 14 concentration. So, the question is the manuscript authentic? So, the museum got a manuscript claimed to be by Leonardo da Vinci, and they spent the paper for this testing and learned that 97.4% of its initial carbon 14 concentration, and they want to check that whether the authenticity of this manuscript. So, we have the governing equation AT is equal to A0 e to the power minus lambda t, where your A0 and sometimes denoted by A0, it is the amount of carbon 14 present in the sample when it was discovered, and AT is the amount of C14 present in the sample at time t. Now, here this lambda, it's the rate of the decay. So, we calculate an expression for half-life, which is the amount of time required by the decreasing substance to reduce to half. So, I have AT equal to A0 e to the power minus lambda t. This will be reduced to half at some time tau, and I have e to the power lambda tau equal to 2. This will give me lambda tau equal to ln2, and this will give me lambda equal to ln2 by tau. And half-life of C14 is 5730 years. So, we can get the value of lambda. Now, from the governing equation, we have AT equal to A0 e to the power minus lambda t. This will give e to the power minus lambda t is equal to AT by A0. And we get this value to be 97.4%. So, I divide by 100, and this will give me 0.974. So, this will imply minus lambda t equal to ln 0.974, and this will give minus the t equal to minus 1 by lambda ln 0.974. If you substitute, it is minus 1 by. So, from here the value of lambda is tau divided by ln2, and ln 0.974. So you get minus 5730 divided by ln2 is 0.693 and ln 0.974 will be given by minus 0.02634, and this value is approximately equal to 218 years, and that is the age of the paper. So, this paper is made, so that it went to the lab for the lab test in 2022, and if the 218 years, if I subtract, so I get this is equal to 1804. So, this does not fall in this period, and hence the conclusion is that the manuscript that is claimed to be of Leonardo da Vinci's is not authentic. So, that is how you test a sample and check the authenticity of a relic or a fossil or a bone like that. Let us take another example, say this Shroud of Turin. So, the problem is that the British Museum was authorized in 1988 by the Vatican to find the approximate date of this relic known as Shroud of Turin. So, if you can see this figure, so it is believed that when Jesus Christ was crucified, this was the only cloth that covers his body, and there is a mysterious image that has appeared on that cloth. So, that is why it is quite important, and the Vatican wants to find what is the approximate age of that cloth. And the information they have given, that the British Museum, the reports confirm that the cloth fiber contains 92% and 93% of their original carbon 14. So, what will be the approximate age of this Shroud of Turin? So, that was the challenge that was placed before them, and they use this method of carbon dating. So, if we do that, so we have this half life lambda is equal to 1 by tau ln 2. So, if I put the value of half life of carbon 14, it is 5730, and this is approximately will be equal to 0.000121. So, I get my formula A t equal to A0 e to the power minus lambda, which is 0.000121 t. So, I get t equal to minus 1 by 0.000121 ln A t divided by A0. So, this is now my formula. So, in that formula 1 by 0.000121 ln A t by A0, I have the information that contains 92 and 93%. So, they gave an approximate value. So, what is my T1? So, if I substitute minus 1 by 0.000121 ln, this is 0.92, and that will approximately give me 689 years. And if I put the value log of 0.93, that will be approximately giving me 600 years. So, they were authorized in 1988. So, if I write 1988 minus 689, that gives me 1299, and 1988 minus 600 gives me 1380. So, they give that okay, the Shroud of Turin, it is between 1299 to 1388 AD. So, that is how we calculate using mathematical model and this technique of carbon dating to approximately find the age of a particular fossil or relic. In this case, it was Shroud of Turin. So, with that we come to the end of this lecture about the mathematical model of this carbon dating. In the next lecture, we will take up some very interesting models. Till then,